So this is the Tanabe air compressor, and inside here we have the first stage suction discharge valve, as you can see here. Let's check how compressed air is produced on this vessel. Compressed air, in my opinion, one of the most used tools on the vessel. It's simply the air all around us with some extra energy. We use it on board for many things, such as cleaning, powering pneumatic tools, remote pneumatic devices, and even starting the main engine. So let's check out the basic overview. We obtain compressed air through these air compressors. On this vessel, we have two types: the main air compressors and the service compressor. The main air compressors compress air to about 30 bar pressure. This is very high pressure that can be used in starting valves in the main engine to break its inertia. Then we have the service compressor, which compresses air to about 7 bars, which is later used in our service and control air lines. Air compressors have a few components and need 4 things to function properly. Let's check them out. First, electricity to power its electric motor and solenoid valves. Then, cooling water to cool the compressed air between stages. More on that later. Lube oil to keep all mobile parts lubricated, and obviously air that's all around us in order to compress. Here are some key components to have an idea, but don't worry. As always, we'll go step by step. For better understanding, let's together check out the flow of air in the compressor. First, air will enter the compressor through this suction filter due to the suction created by the reciprocating double head piston in the cylinder. Here we have a suction discharge compound valve. As you can see here, in the center, there's the inlet portion, which will take atmospheric air, and as the piston rises, the inlet portion will close, compressing the air, and the discharge portion opens, allowing the air to move to the first stage cooler. I'll explain more about the compound valve in the next compressor video, but for now, let's move on. Compression happens just like in the engines. As the piston rises, the inlet portion of the compound valve is closed due to its design, and the air with no way out starts to be compressed. This compression causes the air to increase in pressure as well as in temperature, and in a compressor, this can be as high as 200 degrees. Therefore, we need a way to cool this air down, which is where this air cooler and moisture trap come in. Cooling water from our low temperature cooling water system lower the temperature of the compressed air, thereby also decreasing its volume, allowing more air to enter the second stage. And any moisture or water particles are separated in the trap, due to water being an incompressible liquid, and any water inside the cylinder could cause damage. Here is the second stage inlet valve, which is after the first stage intercooler. As I said before, this is a double head piston, where the bottom head has a smaller surface area in order to compress to higher pressure. So when the piston goes up or compresses the first stage air from the second stage inlet is sucked in, as you can see here. Then, when the piston goes back down, This air is compressed even further, leaving through the second stage delivery valve. After that, the air passes through another cooler called an aftercooler in order to cool down the very high temperatures created, along with a drain to the unloader magnetic valve. I'll explain it in a moment. But finally, this second stage compressed air will then go through a non-return valve to our reservoirs after passing through an oil-water separator. Here we can see 3 different reservoirs. They are the containers of our compressed air. The main ones are filled with 30 bar pressure, whereas the smaller one to 7 bar. This is important because our compressors work based on the pressure inside these reservoirs, using these pressure switches and transmitter. When the pressure drops to a certain point, the compressors start automatically and supply compressed air to the bottles until the stop point pressure is reached. After the compressor is stopped, let's check out this unloader magnetic valve I mentioned. If after stopping the system, there's still compressed air in it, then you can see it creates a back pressure, and not only in the second stage, also on the first stage. And if the compressor were to start in this condition, it would have an increased load due to this back pressure, giving resistance to the piston and electric motor. This resistance can cause overload alarms to the electric motor. Therefore, to remove this load, we have drain connections in both points to this unloader valve. During the first 10 to 20 seconds of compressor running, depending on the timer, this drain is open and all compressed air is drained to our separated bilge oil tank, thereby allowing resistance-free compression until its solenoid valve automatically shuts the drain until the compressor stops. I'll go over this unloader valve in detail, hopefully in the future. So to finalize airflow, it's important to note that the amount of pistons may differ depending on the compressor model, but they're all doing the same process. That means more pistons just mean more flow, not more pressure. Okay, then we have the cooling water flow, which is pretty straightforward. It flows through the inter and after coolers and then to an outlet, going back to our low temperature cooling water system. To ensure that water is flowing, check the pressure and these balls to make sure that they're floating. And finally, the lube oil flow, where we have a wet sump connected to some filters and a pump. This you can see in a previous video. Anyway, we have a pre-filter strainer, then a lube oil pump connected to the crankshaft, a fine paper cartridge filter for small particles, and a cylinder lubricator. The lube oil pump supplies to the crankshaft and its bearings, whereas the lubricator gear pump supplies to the cylinders in both high pressure and the low pressure side to maintain it lubricated and avoid piston seizing.